And we're back, physics students, with episode 5, finally, Newton's second law of motion. Now, Isaac Newton was the first to connect the concepts of force and mass, producing acceleration, which is why we call it Newton's second law of motion. Now, what is Newton's second law of motion? The second law relates acceleration to force, and here it is. The acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. Now, what the heck does that mean? Let's break that down a little bit. There are three key parts to the second law of motion. The first part, the acceleration produced by a net force on an object is directly proportional to the net force. That's part one. That means that if you have a net force on an object, if you have, say, a net force on a rock that's falling from the sky, the acceleration produced by that force is directly proportional to the net force. If you increase the acceleration if you increase the net force by 3 times, you're going to increase the acceleration by 3 times. The acceleration produced by a net force on an object is directly proportional to the net force. Part 1. Second part. The acceleration produced by a net force on an object is in the same direction as the net force. Whatever direction your net force is pointing in, that's going to be the direction that your acceleration is pointing in. We'll cover this in more detail in an example in one more slide. Third part. The acceleration produced by a net force on an object, it is inversely proportional to the mass of an object. Why? Mass is an indication of an object's inertia. The more mass, the more inertia an object has. The more mass of the object, the lazier the object is. And so it's going to resist changes to its motion more. That's why the acceleration produced by a net force on an object is inversely proportional to the mass of an object. A reminder that inversely proportional means that if you increase one quantity, you decrease the other quantity. So if you increase the mass of an object and keep the force the same, the acceleration is going to decrease. If you increase the acceleration and keep the force the same, the mass must have decreased. That's what inversely proportional means. Increase the mass by 3 times, the acceleration is going to decrease by 3 times. If the mass increases by 3 times, then the acceleration is going to be a third of what it was before. That's what inversely proportional means. And that is the second law of motion. Now, why do physicists use math? Because with a very simple equation, we can boil down that really long sentence into an expression as simple as the one that you see here. In equation form, acceleration is equal to the net force divided by the mass. That means that the acceleration of an object with a net force acting on it, the acceleration is directly proportional to the net force in the same direction as the net force and inversely proportional to the mass. That's what that equation means. It actually boils down that really long sentence into a very simple equation. Now take a look at the example. If the net force acting on the object is doubled, the object's acceleration will be doubled. You can see that from the equation. If the net force is doubled, then the object's acceleration is going to be doubled. Oops. If the mass of the object is doubled, however, you're going to have 1/2 of the acceleration. Here we have some more examples. Let's say you're pushing a brick along a table, along one of your lab tables. First example, the force of your hand accelerates the brick. If you apply twice as much force, you're going to produce twice as much acceleration. Still the same brick, so you're keeping the mass the same, and you're just doubling the force. Therefore, twice as much force produces twice as much acceleration. The net force is directly proportional to the acceleration. Double the force, double the acceleration. Third example, however. Twice the force on twice the mass will give you the same acceleration that you had in the first place. Why? Well, you're doubling the force, yes. And you would think that that would double the acceleration. But you doubled the mass as well. If you double both of them, the effect cancels out and you get the same acceleration. I hope this is starting to make some intuitive sense. If not, pause the video and think about these examples. Go back maybe and take a look at the equation again. Now let's say, again, you have the force of your hand accelerating the brick. Now keep the force the same, but change the mass, and you're going to have 1/2 as much acceleration. Keep the force the same, and triple the number of bricks, you have 1/3 as much acceleration. The acceleration is equal to the force divided by the mass. If you keep the force the same, but triple the acceleration, or triple the mass rather, by tripling the number of bricks that you have, you get 1/3 as much acceleration. I'm back, which means that it's your turn. Now consider a cart pushed along a track with a certain force. If the force remains the same while the mass of the cart decreases to half, the acceleration of the cart what? Remains relatively the same, halves, doubles, or changes unpredictably. Pause the video now while you decide what the correct answer is. Ready? If the force remains the same while the mass of the cart decreases to half, the acceleration of the cart doubles. Here is why. Acceleration equals net force divided by mass. Mass is in the denominator, so acceleration increases as the mass decreases. If you have the mass rather, then the acceleration will double. Let's actually try it out with some numbers. Let's say that you have a force of 1 Newton and you have a mass of 1 kilogram. You will have, with the force of 1, if you have 1 Newton force and 1 kilogram of mass, then the acceleration of your cart is going to be 1 divided by 1. It will equal 1 meter per second squared. Let's say, though, that you have the mass of the cart. You decrease the mass of the cart, and so now the new mass of the cart is 1/2 kilogram. So m equals 1/2 kilogram. If you put the numbers into your calculator, you will find that the acceleration becomes twice as much. The acceleration will now be 2 meters per second squared. Try it out. You've kept the force the same, but you've halved the mass of the cart, therefore you double the acceleration of the cart. Your last question for Newton's second law of motion. Push a cart along a track so twice as much net force acts on it. If the acceleration remains the same, what is a reasonable explanation? The mass of the cart doubled when the force doubled. The cart experiences a force that it didn't before. The track is not level, or friction reversed direction. Read the problem carefully. Push a cart along a track so twice as much net force acts on it. You would think that if you have twice as much net force acting on the cart, the acceleration should double, but the acceleration remains the same. What's the explanation? Pause the video now as you decide. The explanation is that the answer is that the mass of the cart doubled when the force doubled. And here's why. Once again, acceleration equals net force divided by mass. If you double the force, you should double the acceleration, but it doesn't, so the mass also has to be doubling to cancel out the effects of the force doubling. If you have 2 times as much force and you have 2 times as much mass, it cancels out and you have the same acceleration that you had before.